Okay, so good afternoon, everyone. So I'm going to talk about scalable infrastructure for personalization. Before that, so I'm a research director at INRIA in France, and I'm leading a group of about 20 people on large-scale distributed systems, basically, both theory on the theory side and the practical side. So what is INRIA? Just I'm not going to bother you for long with this, but this is this is where we are. So this is France. For those of you who do not recognize this shape, this is Paris. And actually, I'm coming from this place. So basically, INRIA is a research national institute. It's a public institute where hiring basically researchers. Most of our labs are joint labs with universities. So we do have also PhD students in our groups. We do have assistant professor in our groups as well. And there are 8 centers disseminated all over France, basically, and one is in the west. It's a pretty big lab. We're about 600 people. And this is where I'm coming from. And basically, the name of my group is called ASAP, so for as scalable as possible. And we're interested in, large-scale system and peer-to-peer systems and everything. Okay, so basically, this is pretty much, so going back to the topic, today's topic, this is pretty much where we are right now, where, we are kind of almost drawn into a large number of information from different places, like social networks, collaborative platform, whatever you can find on the web today. And although this is extremely useful for many of us, and you can find a lot of interesting information, there is this feeling actually comes very quickly on the user experience, and it's actually the case for most systems, including the one that are already sort of personalized. So if you think of a social network, in a way, you already personalize your social network, right? Because you kind of chose which neighbors, which friends you wanted to have. And regardless, it can be the case that you're actually overwhelmed by a number of information just because the friends that you were supposed to have suddenly are very prolific with respect to information. And actually, more and more, you have some advertisement also in the news feeds of social networks, and basically you can be drawn in a lot of information. So there is clearly a need for personalization in this spectrum. And what I mean by personalization, I mean there are many ways you can do it, and I'm sure you guys know, some of you know exactly how to do it. But what I'm in that context, what I'm saying is that trying to give the right information or the information as right as possible to the user whenever they are navigating on the internet. So that can take the form of different things. That can be in the context of social network, that can be in the context of recommendation system, that can be also in the news dissemination system, and so on and so forth. So personalization is actually something which is very difficult, and the main basically issue with this is that we have to deal with a huge volume of data. And out of this huge volume of data, there is only a very small portion which is of interest to you. Your interest can be dynamic. So in a few days, I'm sure you haven't missed this, there will be the football World Cup. Now, this is something that, personally, I'm not into football at all. But, maybe for this specific occasion, I might have some interest in watching some of the games. So in that case, I couldn't say that football is a sustainable interest, but that can be the case for a few weeks. And the other thing is that the interesting thing that are good for some users, it does not always come from friends. So it's not because you have picked already the people that should, give you some information on a social network or in whatever collaborative platform that the content is going to come from there. And actually, it's very likely that you resemble your friends in a way, and then they might not give you some interesting information. Not always. Now, there are a number of systems that do personalize in a more static version, and this is what you have for publish subscribe systems, where you subscribe to some events or pattern of events like RSS feed or this kind of stuff. Now, those things have a very specific granularity. So again, if I register to some RSS feed in sports, then I'm going to get pretty much everything about sport. Now, if I want to narrow down this and go into volleyball, then I might miss whatever information that's going to happen in football in the coming weeks. So basically, the granularity is not always the one that you're looking for. Anyway. So what I'm interested in this spectrum is basically more than how you can personalize exactly a system. Is like, given that you have a way to personalize a system, how you can build how you can build a scalable system that can handle a large volume of data and, more importantly, an extremely large number of users. And basically, I'm interested in the very specific problem of k-nearest neighbors computation over large data. So everybody is familiar with k-nearest neighbors computation, pretty much. Yes, this is what I'm saying. So this can be used in a large number of things. And actually, the one that I'm going to be interested in is collaborative filtering. Okay. Again, the goal here is not to find new way to do it, but efficient way to build a KNN computation network on top of this. Now, how do I do this? So basically, the goal of this k-nearest neighbors topology that I want to build is that I want to provide, so I have a set of users, they all have some profile of some sort. That can be, their navigation history, that can be the thing that they liked on a given social platform or whatever. And then I want to provide each user with a set of neighbors which are the closest to her interest. Okay. Now, of course, as the system evolves over time, I want the topology to reflect these changes. Now, I want to basically, and then once you have this topology, you can use it for a number of things, okay? And including, you can use this for disseminated information, you can use it for recommendation or whatever, okay? So I'm placing the context of this talk here is carrying nearest neighbors topology for this. So now, and this is something that I borrow from someone that a professor from MIT that I attended a talk of recently at TPFL actually, and so everybody is talking about big data. Well, at MIT they talk about truly big data, and this is really what I want to talk about today. My background is very much into peer-to-peer systems, okay? And what I think really is that in a peer-to-peer system, which is a system, so everybody knows what a peer-to-peer system is, right? Yeah. So in a peer-to-peer system, just because the way you design some systems, so basically in such systems, every user or every client can be a server. Okay, that's the definition. So that scales well because as you increase the number of clients, you increase potentially the number of users. Okay, now you can use peer-to-peer infrastructure for a number of things, and actually, some very well-known company used this initially, such as Skype, for instance. And what I really advocate here is that by design, this infrastructure is scalable. Right? And if you think and if you design algorithm that way, then it's very likely that they're going to scale in semi-distributed infrastructure, but also even centralized infrastructure. Okay, so basically the first part of my talk is going to tell you how to build this kind of k-nearest neighbors construction in a fully decentralized way. Right? And then after, we're going to go into how we can apply this in a less decentralized way, but still distributed. And the key to this is that you don't want to look for everything. You don't want to be exhaustive in the computation that you want to do. So basically, when it comes to computing your k-nearest neighbors, okay, the brute force approach would consist to compare yourself and compute your similarity with any other user in the system, for instance, and actually. This is typically the kind of thing that you cannot do in a peer-to-peer system, right? Because there is nowhere in a system where there is a global knowledge available, at any given point in the system. So instead, each node and node/user has to, come up with individual decision, and the system as a whole needs to converge to whatever global service you want to achieve. And the key also to scalability in this k-nearest neighbor construction is exactly to do this, not to try to compare your similarity with every other user in the system, but just pick the right sample. Okay? Now you can take a random sample, and that's going to take a while, but you can also be a little bit smarter in the way you do it. And this is what I'm going to talk about right now. So basically, now I'm going to show you how you can build a k-nearest neighbor graph, okay, in a large set of nodes without any server, right? So the first thing that you want to know is basically which are the right nodes, and this is just about a similarity metric. Again, contribution is not really here. I mean, there is many ways you can do it. And that means that whenever you encounter a given node, you can decide whether it's close or not, or at least whether it's closer or not than another node. Now the big question is how you can discover them in an efficient way, okay? Again, in a peer-to-peer system, there is no way you can have the global information everywhere or even anywhere, okay? So no user in the system or no node in the system actually has the global information. So you need to find a way to discover your close neighbors without basically going through computing your similarity with every other node in the system, just because you don't even know every other node in the system. Okay, so basically with respect to the which node are close, we are considering a system here where you have a bunch of users, a set of users here, a set of items, okay? And then the profile of a user is actually the vector of items that have been either liked or shared or viewed, or that very much depends on the application. And each time I will present some evaluation, I will go back to exactly what the profile that I'm looking at. But this is very standard kind of building profile of users. Now then you can use different kind of metric. And what is interesting here is in this system is that we don't really care at this point. We are considering user-based kind of collaborative filtering approach where we don't really care of what is the content. It doesn't mean that it doesn't make sense, but that's what we're doing right now. And actually, if we go back to collaborative filtering approaches, one reason why user-based collaborative filtering approaches are not always used as much as the item-based is also because of the scalability. And I'm sure you guys here have a lot of experience with this, but every time you kind of crawl some data set, there are many users than items, okay? So whenever you want to compute the KNN graph for users, then it takes more time and it requires more computation than when you have to do it on an item-based model. But then again, when you're in a fully decentralized system, it's very natural. So first of all, it's very natural to do it on a user basis because basically each user has to take care of her own data. And then the second thing is that we can do it because of the scalability property of these systems. So far so good. Oh, so if you have any questions, just ask me. You're very much encouraged to ask me during the talk. Okay, now how we can discover them. So now basically what we have is that we have user, they have profile. Okay, this is one user, a machine, one user, one machine kind of setting. And basically the goal is to, whenever you find a user, you know how to compute the similarity. Now the question is, how can I find these users? Okay. So you have to remember that in a peer-to-peer system, nobody basically has the first thing that you need to maintain is connectivity in the network. Okay, so you have internet, you have nodes connected on the internet, and basically what you want to do is that you want to organize these users in a system which is connected. Okay. So in addition, you want to do it in such a way that it can be useful for building the k-nearest neighbors computation. So basically, the first thing that you want to ensure is you want to connect your neighbors, and we do this using some gossip-based protocol. So this is all protocols are described in this ACM Talks paper here, and so the goal is to build a random graph, okay, a continuously changing random graph, okay, in such a way that at each cycle, say, each node will be connected to a set of other nodes which are picked uniformly at random in the system, okay? So it's like with this kind of graph, the functionality that you have is that at any moment, I'm going to have a sample of the system which is uniform, and which will change every so often. Okay, so this is a dynamic graph. But what you ensure is that with this kind of protocols that you actually have a connected graph. Okay, so that means that this is a connected network of nodes, and that nodes which are no longer connected, or which are dead or faulty or whatever, are out of the system. How do we do this? Each node, so consider these two nodes P and Q. Each node has a set of, so in that case it's 5 neighbors. Okay, those are uniform random neighbors. Okay, now periodically so Q is one of these neighbors of P and the other way around. Okay, now periodically each node will pick at uniformly at random one of its neighbors, and basically they're gonna exchange their neighbors. Okay, so the goal by this is that you kind of shuffle the network every so often, and the goal is that you don't have a static network. And at this occasion of node exchange, what you are going to do is that you are going to get rid of nodes which are faulty or which are not in the system or whatever. So basically, if the node that I'm trying to contact is faulty or doesn't answer, then it's going to be it's going to be disregarded and considered as faulty. So basically, based on this, all these two nodes have some. So I'm not going to go into the details because that's not the goal here. But I mean, there are some specific way you pick those nodes and specific way you can merge. But roughly speaking, what you can see is that at the end of this exchange, okay, you will have a large number of nodes, and the goal is to go back to your five numbers. So basically, you will just truncate this big list. What that means is that after this peer exchange here, P has some new neighbors. It has some old neighbors, but also in that case 3 new neighbors, and Q also has 3 new neighbors. Okay, so this actually is very useful because that provides a way to sample the network. What that means is that every time, as time goes, every node is going to do this kind of exchange with its neighbors, and this is a way to sample the network. Well, that's very good because this is an opportunity to discover nodes that can fit in my k-nearest neighbors topology. So the result of this is that you end up with a uniform random graph, okay, which is very resilient against churn because because you keep changing and you keep shuffling, then you have a dynamic network of correct nodes, and with a small diameter, which is good for exploring the network. Okay, so this is the underlying situation. Now, on top of this, what we're going to do is that we are going to compute the KNN topology. And we basically do it exactly the same way, except that in the case of the KNN topology, there is a convergence. Convergence happens eventually. So if you're in a static system, you will have, you have a set of neighbors which actually match your requirement, and that's not going to change over time. So at some point, you're going to converge. So basically, 2 neighbors which have already computed so here I'm talking about the KNN neighbors, okay, not the random ones. So basically, this Alice here has 2 neighbors, Frank and Ellie, and Bob. She will contact Bob to basically see whether his neighbors are good for her. If that's the case, then there will be neighborhood optimization on this. Okay, so this is a very simple way. Now again, this is extremely simple if you have a sample facility in your network, okay? And again, this is exactly what the underlying protocol gives you. But if you rely only on this underlying protocol, what happens is that you will have a random sample, okay? So the way to actually grab the right nodes is the complexity is actually the size of the system. Okay, which is not extremely good. It's like you standing somewhere at, in Moscow, in a very famous square, and you take the assumption that everybody is gonna come by you, and then each time you compute your similarity, so eventually you will have seen everybody, right? But that will take a while. So instead, what we're doing is that we have a 2-layer protocol in which there is this underlying random peer sampling protocol where this graph keeps changing and is a random graph. And on top of this, there is a clustering protocol, which is another protocol. And the idea here is that instead of picking a random node and decide and explore his neighbors, I'm gonna take a neighbor which is already in my nearest neighbors. So I have, which is very likely to have neighbors that are good for me. Okay, if Rashid and I are close in this network, his neighbors are going to be good, are likely to be good for me. Okay, more than random guys. So we have this two-layer infrastructure here, and what you can see here is exactly. So this is the. So this is in cycles. Okay, this is a system of 10,000 nodes, and here what you have is that the current. The ratio between the ideal neighbors and the one that you have in your KNN topology. And what you can see is that if you just rely on the random sampling, you will eventually converge, but it's going to take a while. Now, if you bias your sampling by having these two protocols running and trying to achieve your KNN using, if you come back to this, using this topology and not only the topology down, then you speed up the convergence a lot, and then you have very quickly you converge towards your the right KNN topology. Okay, here 100 means that you have the right KNN topology. Okay, so you can use this for a number of applications, and again, we use this in the context of decentralized news recommendation, which is what I'm going to talk about here, which has been published by EDPS, some top K protocols or geo-recommendation protocols, but really what I want to talk a little bit about now is this decentralized news recommendation system. Okay, so far so good. So we have a random topology and we have the KNN topology, and now we want to use it for some application. And the application that I'm going to use is a decentralized news recommender. Okay, what is it? Why is it motivation? Is that at some point, well, maybe 10 years ago, people would navigate the internet by searching the web, okay, using search engine. They still do. So your business model is not over, but not entirely. And actually, notification as take is now very important. Okay, it's very often, and you can do this exercise for yourself. It's actually very often that you navigate on the web just because you saw a link somewhere on a collaborative platform or on a social network or whatever. Okay, now. This is what we are trying to do, is that instead of having some news systems which is the same for everybody, or which would put at the top all the which is pretty much what's going on today on newspapers, right? You have the same first page for everyone. So sometimes you have some specific list of items which are like the most shared or the most viewed or the most commented or whatever. Sometimes you do have some personalization, but it's not that often. So in this system, what we're doing is that we would like to provide some personalized recommendation by having here the news that have been of interest from the people from your nearest neighbor topology. Okay, so this is very much collaborative filtering. Okay, recommendation using user-based collaborative filtering. Now, what is original is that it's fully decentralized. There is no server here. Okay. Now, the way it works is that you can see this as an implicit notification system. So it's like a publish-subscribe system, in which you don't even have to register. Okay, you don't even have to subscribe. It's gonna come, hopefully. So it's not 100% hit ratio, but it works. It doesn't work. Not too bad. How does that work? Basically, there will be, so there are two things. The first one is how you compute the graph. We've seen how we can compute the graph. And the second thing is that how you disseminate the information on top of that graph, okay? Now, the main knob is going to be the user opinion on some specific piece of news, okay? So basically, whenever, as a user, I'm going to receive some news items. Sometimes I like them, sometimes I don't like them. We can discuss on what is the best semantic to say I like, I don't like. Okay, that's not the point here. In the context of that talk, I'm going to say if I like it or if I click on like, then I like it and I want this. It matches my interest. If I don't, it doesn't. Now, when a user likes it, then that will generate that will update her profile. Okay, and this is used for the k-nearest neighbors topology, the same way I just described. But in addition, what we are going to do is that depending on the user opinion, the dissemination protocol is going to be different. So if I like it, I'm going to very naturally try to send it to the people who look like me. If I don't like it, in a standard collaborative filtering approach, I would do nothing. Okay. In this case, I do something. I send it to people who are not in my in my interest-based neighborhood, but who might still have an interest in that news. That gives an opportunity for that news item to still travel in some part of the network when it can match some interests. What is tricky in that case is that you have something which is extremely intricated, basically intertwinkled. Okay. Basically, your graph is the one that is used for the dissemination. So obviously, the way the graph is done influences the dissemination. Okay, if I'm connected to some people who are very well connected between them, you know, this is going to be a very close circle of users. Okay, so dissemination here is going to be very different than in a system where I would be connected to almost random users. At the same time, the way the dissemination is done is going to influence the topology, okay? Because depending on how the dissemination is done, this is how my profile is achieved, okay? And then this is going to influence the topology. So in other words, you have to be very careful, because if you keep sending information to the same set of users, basically the similarity is going to grow, okay? And not only it's going to grow, but almost artificially, in the sense that other nodes won't even have the opportunity to like this item because they will never receive it. Okay, so you will grow into very, you know, isolated island of users with similar interest and more similar in a way. So this is something that we're still working quite a lot on how to model this, and this is extremely complicated. I mean, one of my researchers is, world champion of randomized algorithm in my group, and still he has very hard time because it's very dynamic and it's very difficult to analyze. Okay, so basically, again, if I want to summarize what we do, when we disseminate, so again, KNN computation is achieved exactly the same way as I explained before. Now, dissemination, it hashes that way. There are two questions we need to answer. To whom, and to how many nodes. To whom, basically, whenever I like it, I'm going to send it to my friends, basically the people who are in my KNN graph, okay? Now, when I don't like it, I'm going to forward to random users, okay? Again, this is to address the serendipity kind of thing, okay? I'm still give a chance to that news item to travel in the network. Now, the question is to how many. We know in a random graph that if you send an item to about log n other nodes picked uniformly at random, you know that you're going to reach with a very high probability, almost. Well, you're going to reach all nodes with a very high probability, okay? Now, this is not exactly what we want to do, because what we want to do is that we want to do this in our cluster of interest, okay? So basically, this is this log n that we're going to use on the when we like an item. So basically trying to reach out all the nodes in our cluster. Note that the n here is the size of the system and not the size of the cluster, because that would require to know the size of the cluster, which is something dynamic and not always easy to compute. Again, we're in a decentralized system. And then whenever we send this, when we don't like it, we send it to a random user, but basically to a very small number of users. Otherwise, we're going to reach everyone, okay? So it's like 1 or 2. It depends on the size of the system. So now I'm just giving you some, so the way we did it, we have a lot, I have other evaluation, but what I'm showing here is a survey of real users. So the way we did it is that we bothered friends and family for a while and give them a list of news items with some, basically asking them to say whether they liked it or not, okay? And this, based on this, we basically did the A/B test. Well, cross-training testing. Like we used 50% of the profiles to train the system, and the other 50 to evaluate the precision and the recall. Again. So we compare with the standard gossip protocol, where each recall is very good. So gossip protocol is that you have a fan out of 4. So basically, each time you receive an item, you send it to your friends. with a fan out of 4, and this gives a very high recall because this gives a very high dissemination property. Okay. Now the precision is basically the average precision that you would have between two users who would send each other all items. And you end up with a lot of messages because basically you have a lot of redundancy in such systems. Okay. Now, this is a cosine similarity-based, user-based collaborative filtering system in which whenever you like an item, then you send it to your friends. When you don't like, you do nothing. And here you can see that you improve quite a lot the precision, but now the recall is decreased, is decreased also because you don't reach everybody. And then WhatsApp, which is the name of this recommendation news recommender, we can see that we actually are not as precise as the cosine-based similarity collaborative filtering system, but not that far. But then we're better on the recall side. I'm sorry, this is in the process of from the French to the Russian laptop. There are some weird things appearing.
Can you tell a little bit about precision numbers? Why is it, well, relatively small?
Well, this is very This is very dependent on the data set that we use. Okay, and actually it's extremely. You know, this set of there was like 100 items that we put were like kind of random things, okay, and then it's extremely. So this is why we put this collaborative filtering here, because it's you can compare these values. Now it's very difficult to compare from one data set to another because it's small and it's very specific, okay. Now, if you look at another data set, and then you will have. So, I do have some other figures on other data sets, and basically that shows. So, the main difference in between collaborative filtering here and what we're doing, yeah.
I think I understand correctly. Do you consider only 480 users, or
yes.
do you consider 480 users in the big network?
No, just those ones. Those ones, yeah. This is a small network. Again, I have other figures, right? But I mean, this, you know, the thing is that when you take another data set, like a real data set, that's fine. We did this. For example, we crawled dig, okay? Now, the issue is that what is very difficult to evaluate is that if our system would recommend the news to a user, okay? Well, maybe that wasn't a bad idea, and if that user would have had that news, he would have liked it. But then there was no way with a crawl data set that you can do it. So, but we did it as well on other data sets, and yeah. Now, this is just to show you that, you know, how many news items that were that benefit from the unlike dislike kind of feature. Okay, so again, a collaborative filtering technique, just plain, wouldn't have this dislike option. Okay, either you like it and it's sent to your friends, or you don't like it and we do nothing. Okay. Now, what we show here is that this dislike option actually counts for not too bad. So this is a number. Again, this is kind of this what happened in the process. But take a look. This is a number of dislike. Okay, that happen on the path of a news item. Okay, so you have a news item traveling in the network. For a given news, it can follow several paths, right? Now, this is the number of times that there was a dislike. So, for 31% of the news that have been liked by users, there was one dislike, which means that it is worth doing it. It is worth giving a chance to news item to travel a different part of the system. Okay? Tu peux me dire là, s'il te plaît? Okay. I'm running out of time already. So this is, I'm just going to go through this quickly because this is some other evaluation. One of the things that I wanted to say is about privacy. Okay. Now, in a server-based system, let me do this first. In a server-based system, okay, you're not, as a user, you do not hide a lot from your server, okay? And this is precisely why users give away a lot of information, and precisely why we can actually enjoy some personalization features sometimes, okay? Now, in a peer-to-peer system, you basically protect users are protected against server big eyes kind of thing. Okay. Now, what they are not protected against is other users. Okay. And why? Because each time you want to compute your similarity in such a network with some other user, you give your profile, and then people compute that similarity. So if you want, that might be some privacy breaches for a number of people. Now, in the context of our news recommender, there are two ways that there are two at two places we can learn about the interest of a given user. Okay, the first one is obviously during this user clustering phase, when you compute your KNN computation. Just because you exchange your profile in clear, that's enough to gain some information. So, okay, that's one thing. Now, even if you were to solve this, it's not enough, because there is a predictive nature in our protocol, in the sense that we know that basically when you like it, you send it to your friends, and you know that when you don't like it, you send it to a random node. So just by getting a news item from a given node, then that would be an issue. So there are several ways you can there are basically several ways you can fight these things, and in this context, we've been doing plenty of different things, including very heavy, a crypto-based kind of protocol. But we also here, what I'm going to show is a very lightweight way of hiding some information, is by obfuscating the profile. Okay. And now for the second thing, what we're doing is that we just randomize a little bit the dissemination. So we add a bit of randomness in the process, so that then it's very hard to conclude on anything. Now, the property of obfuscation is that, first, it doesn't reveal the exact profile, because we kind of hide a number of things. And second, when it reveals stuff, it reveals the less sensitive information. So I'm going to show you how. Now, the randomized dissemination in that version is very simple. We just flip the opinion of a given user with a given probability. Okay. So obviously, if you flip the opinion of you flip the opinion for the dissemination protocol, meaning that there is an item, I like it, I put it in my profile, I obfuscate my profile and everything. Now, whether I like it or not, or whether I will forward it to my friends or not, this is what is going to be the result of the coin flipping. Okay? So if you do a 0.5 coin flipping here, probability, then you do whatever. You maintain the highest privacy level in a way. Okay? But you also very much randomize the process. So you will lose, again, there is no free lunch, right? If you want to have a lot of privacy, then you will lose on utility of whatever mechanism you're using, and the other way around. Okay, how do we do this? So the first thing that we do on the profile is that we build some compact profile. So private profile is this green stuff here, and this is a full information about the interest. This is what users store at their own machine. Okay, compact profile is what they are going to. This is a compact version of their profile, and this is, you can see this is a Bloom filter. Okay, so basically you just aggregate the signature of the item that you like in this. Okay, now what is good as well is that it restricts the size of your profile, and because we are in a network, in a large-scale network, you might want to reduce the number of information that you have on your profile. So these are the stressors. So bear with me for 5 minutes here. Private profile is all the profiling clear. Compact is the one I just described, which is aggregation of the signature of the item that you like. Filter profile is a profile which actually aggregates the interest of all the nodes that you have in your KNN neighborhood. Okay? What that means is that with this, you actually have an idea of which are the item or interests that are the most popular in your neighborhood. Okay? Now, if you use this as a mask on your own profile, you will reveal mostly what is common to your neighborhood. Okay? Say that you have a neighborhood where a lot of people are interested in computer science, okay? And then you have a very sensitive interest into football, right? Now, by having this mask, you will still hide this interest. So whenever you will reveal, It's already in a obfuscated form, but it will concern the less sensitive information. So obfuscated profile is the one that you send after this mask here. And in addition, we also have an item profile here, which is the aggregate interest of the user that like to give an item on the way. Okay, so say that the news went from myself to Ivan to Rashid. Okay, then at Rashid's, the item will have the aggregation of our 3 profile. Okay. Right, so basically whenever you receive a news item, you put it in your private, you put in your private profile the fact that you like that item. You basically add your compact profile to the news item profile to produce the new item profile, which is going to be forwarded with the news. This also news item profile is going to be used in this filter profile, used as a mask, and this is the obfuscated profile that you will end up. And this is only that one that you're going to send over the network. Now this is the one that you're going to use for computing the similarities, but this one is the one that you're going to send away. Okay. Now, so that was for the profile. Randomized dissemination, again, it's a very simple mechanism where we flip the opinion with a given probability. And basically the private profile here will actually we still keep this information in the profile. So you could have another version which is completely which would also use this coin flipping to update the profile. Okay, we don't do this. That would be yet another level in the privacy, okay? In the sense that you really obfuscate the whole thing. Not only you flip the coin to say that you decide to like or not an item for the dissemination, but also for the profile building. We don't do this. Okay, so in this context, we did the same experiment on the same data set, approximately, or another version of this real data set. And this is what you observe. So F1 score is this mixed measure between recall and precision. And what we can see is that actually just by so clear text is whatever you have with a clear text version. This is a coin flipping on the dissemination of 0.5. Okay, so this is what you get, and this is where that evaluates the impact of obfuscating the profile, but not randomizing the dissemination. Okay, and we can see that actually on the F1 score there is not that much of a difference. The difference is mostly on the precision. Okay. And what you can see here, so this is a probability of actually, so clear text is here. Okay, sorry, here in black. And then what we can observe is that as you increase the probability to disseminate or not an event, you are going to basically lose a little bit on precision. But it's not a huge impact. Okay, so I think I'm gonna so you can try it if you want. Install this on your machine, and you can try it. I'm just going to give, I think it's about time, isn't it? 5 minutes. So I'm just going to use my 5 remaining, I have 5 minutes, yeah? My 5 remaining minutes to say something about people who are not happy with peer-to-peer. And I know that there are people who are not happy with peer-to-peer out there. And actually the point I want to make here is that this very same algorithm, if you use it in another setting, that works very well, okay? And especially what we've been doing is that we've been using it in a kind of hybrid architecture, okay? And this is what I call the hybrid recommendation engine. And this is how it works. So this is what you have in a decentralized app. So if you were to apply whatever I presented for recommendation, this is the way you would do this. So each user has this local data structure where the profile table and the KNN table, okay, which is basically your neighborhood and the profile of your the people who are in your neighborhood. Forget about privacy in this context. Now, and then you would have the peer sampling to build your random network and make sure that you connect in network. You would have your algorithm to make sure that you can find actually your care nearest neighbors, and you would have an algorithm to do the recommendations. Say the K most popular used items in your user in the profile of your KNN users. Now you exchange your profile, you manage the overlay, and this is how it works. No server, no nothing. Now, but that's peer-to-peer. What we do okay, in a centralized approach, this is completely the other way around. You would have exactly the same data structure, but for everybody, okay? And then a user machine would do nothing, just send some request, and then the server would actually use this global data structure and compute some recommendation and send some recommended item to a user. Okay, this is what is done in a standard user. Now, what you can, and again, I know that people say, well, no, machine now, this is nothing, you know, memory, that's nothing, and you can do real-time computation of huge amount of data. Well, from my experience, that's not true, okay? You have a lot to do, whether if you really want to have real-time recommendation, you have to be extremely careful in what you put in memory, what you put on disk, and everything. So it's not that easy. Now, what we propose in that system, which is called HiRec, for hybrid recommender, is basically taking the best of the two. So the idea is that, so why people do not like peer-to-peer? Because they do not have control, okay? So there is nothing they can do on how to leverage information of the users. Now, why peer-to-peer is good? Because users do some job, okay, and they do some computation, and actually that, you know, alleviate the load of any server. And this is very, this is what we do here. We let, and that's just in the browser, in the browser browser machine, basically. Sorry, in the browser of users machine, that we have a bit of JavaScript going on, and that we basically, based on a restricted number of nodes that is sent by the server, will compute the new KNN, okay, and will compute the new recommendation. So with this kind of things, there is no data which is stored on the server, okay, but the user machine is in charge of computing each time there is a query, computing the new KNN topology for herself, and computing the recommendation again for herself, okay? And the server, in that case, will still maintain the global data structure, so that information can be leveraged with as in whatever server. But whenever there is a request from a client, it will basically send a set of candidates, which is the old neighbors of the KNN, plus the neighbors of the neighbors, and another set of random neighbors, and then, and then this information going to reach that node that will do the computation and basically update the KNN when it's done. So it's actually something that is extremely efficient, and that actually, so this is how it works, okay? This is pretty much what I just said on another timeline kind of thing. And here we use the movie lens data set with, well, 3 versions of the movie lens, and this is the one for the, I think this version here, I'm not sure, or maybe movie lens, the first one. And then DIG also is another data set that we use for the experiment. So in that case, we compute the quality of the KNN view, okay, the quality of the KNN. And here, this is measured at the average similarity that you have in your KNN, okay? So HiRec here with k equal 10. K is the number of neighbors that you want in your network. This is with 20. This is exhaustive, meaning that you actually compute the k best ever, okay? But that's offline. So this is obviously the best one. Okay. Oh, damn it. Okay, which is the purple one here. Our option here with 10 is here. The one with 20 is up here. And that one here is another one with 10, but we force, well, that's a kind of subtlety of the data set. We force each user to update its KNN, because the way it's done here is that we take the movie lens data set. Every time there is timestamp saying that there is a request, we launch a request. But if there is no request for, say, a week, there is no chance for the user to actually update its KNN, okay? And then the view similarity in a way degrades. So by this is by forcing something to happen one iteration of the KNN to happen every week. Okay, this is, and we can see, basically what we can see is that we're very close to having an exhausting thing. Again, this is a recommendation quality, okay? In terms of how many of this is measured here in terms of how many items we were predicting well. Exhaustive best, again, is always the best here. High rec is this red one here. And these two ones here are exhaustive, but with some latency, okay? Because exhaustive best means that you would compute at any time the best K, which is not something you can do, you know, online all the time by having the the best computation. So this is instead when you do it every hour, and we can see that this is pretty much exactly the same results that what we achieve. And every 24 hours, meaning that's an offline computation of the KNN, and we can actually do better than that. So I'm going to stop right now. So if I want you to take away something from this talk is that, you know, by designing your algorithm in a kind of, with peer-to-peer in mind, you can actually go a long way with respect to personalization. So I'll be happy to answer any question you can have. Thank you. Yeah.
Yes. Thank you for very interesting talk. Could you clarify how did you measure quality of recommendations at previous?
Oh yeah. This is basically the number. So we take. In that case, we basically train the system again on half of the profile, okay, and then on the other half, this is an absolute number. We measure the number of recommendations that were based on this number of recommendation. Okay.
Yes.
So this is at each request the number of items that we would recommend, and we just measure how well we did it. It's a brute, you know. It's in terms of, in that case, it's just the absolute number.
Absolute number of good recommendation. So recommendation. Which receive like from.
So you have a profile, okay? You train on half of it, say, okay? Now on the other half, you will predict, so either 1 up to 10 items, okay? If that's in the other part of the profile, you say that's fine. You say it's a good one. This is how we measured it in this. We have other measure in the paper, but so that one is here.
So it's number of items which were marked. Which received good mark from user.
Exactly. Yeah. And again, this is movie length. So movie length is I don't know if you know that data set, but there are some ratings. So we basically assume that everything above the average rate for an item was liked, and the other one was not liked.
Have you compared this approach with movie length approach, with the collaborative filtering algorithm?
We have compared with, we have compared with other collaborative filtering approach. I don't have the figure here because they kind of, again, in the process, some things disappeared between there were some incompatibility. So basically, we compared not exactly with the movie lens approach because they have a very complicated matrix factorization kind of approach. We compare against collaborative filtering other approaches.
Which one?
A standard user-based and a standard item-based, basically.
And could you shortly describe results?
If I what? Sorry, I didn't hear.
Comparison with
well, this is this I don't remember from the top of my head. I think it's in the paper, so I would be happy to send this. But this is pretty much again what makes sense in that case. I think item-based was maybe slightly better from the movie lens. But the user-based, okay, you cannot do better than the exhaustive approach anyway, okay, the way we do it. So really what is interesting here is that by having kind of an iterative approach where you offload some part of the computation of another of the user machine, you end up with something which is close. I mean, in a way, you can see this as a standard collaborative, user-based collaborative filtering.
I mean matrix factorization.
No, that I didn't. Well, that I didn't, because actually one of my students right now is trying to distribute matrix factorization. That's not trivial. Okay, and actually the results with respect to precision, I mean, maybe some are, it probably depends on the data set. But the good thing with collaborative filtering is that it provides good, reasonably good results, and you can actually distribute this in a much easier way, especially with this kind of computation. But no, I don't know if it's matrix factorization. We haven't.
It's not so distributed like
What?
you. Of course, matrix factorization is not so distributed like your approach.
No, exactly. No, you can do it. There are some approaches to do it, but it's not that that easy. Yeah.
Any more questions?
Well, thanks for the talk. You already mentioned this movie lens dataset where they have the rating. My question was, so in your system you have this binary selection, either true or false, and this means that the whole system will, so the system may actually change dramatically when the KNN for one single node changes. The whole system can change dramatically. You don't have this smooth transition from one state to another. Have you considered anything like making the introducing the some scales, like maybe like one of making the selection not 1 of 2 but 1 of 5, 1 of 10 options, and comparing it like, I like this item, I rated this item 2 of 10. Maybe this could make the system more make the prediction better.
Right. No, we haven't. I mean, we basically no, we haven't. We haven't compared with this rating-based approach.
Do you think this can be done, or it is computationally too difficult?
No, I think you can do it. I mean, you won't do it exactly. Well, it's, you can basically, instead of having binary, you can have, it's a matter of putting some weight kind of thing. So it makes the model a little bit more complicated and sometimes less easy to compare with other data set where we had, where we didn't have the notion of rating. So if we wanted to compare, there was no, it was a fairer approach basically to compare with binary kind of ratings. But no, it would just put a weight. Okay, so I think you can, we could achieve this, but we haven't done that. But I think we could.
Okay, thank you.